let's revisit the line integral f dot n ds right over here, because I want to make sure we have the proper conception. And I was a little loosey-goosey with it in the last video. And in this video, I want to get a little bit more exacting and actually use units so that we really understand what's going on here. So I've drawn our path C, and we're traversing it in the positive counterclockwise direction. And then I've taken a few sample points for f. At any point in the xy plane, it associates a two-dimensional vector. Maybe at that point the two-dimensional vector looks like that. Maybe at that point the two-dimensional vector looks like that. And then n is, of course, the unit normal vector at any point on our curve. The outward pointing unit vector at any point on our curve. Now, in the last video, I talked about f as being some type of a velocity function, that at any point it gives you the velocity of the particles there. And that wasn't exactly right. In order to really understand what's happening here, in order to really conceptualize this as kind of flux through the boundary, the rate of mass exiting this boundary here, we actually have to introduce a density aspect to f. So right over here, I've rewritten f, and I've rewritten it as a product of a scalar function and a vector function. So the scalar part right over here, rho of xy, rho is a Greek letter, often used to represent density of some kind. In this case, it's mass density. So at any given xy point, this tells us what the mass density is. Mass density will be in some mass. We're in a two-dimensional world, so it's mass per area. And if we want to pick particular units for our example, once again, this isn't the only way that this can be conceived of. There's other applications, but this is the easiest way for my brain to process it. We can imagine this as kilogram per square meter. And this right over here is a velocity vector. It tells us what is the velocity of the particles of that point. So this is kind of saying how much particles do you have in a kind of a point, how dense are they, and then this is how fast are they going and in what direction. And this whole thing is a vector. It's a velocity vector. But the components right over here, m of xy is just a number, and you multiply that times a vector. So m of xy right over here is going to be a scalar function. When you multiply it times I, it becomes a vector. That's going to give you a speed. And then n of xy is also going to give you a speed. And then it tells you a speed in the j direction, so it becomes a vector. A speed in the I direction becomes a vector as well. But these speeds, the units of speed, so let me write this over here, the unit of speed, so now we're talking about, in particular, m of xy and n of xy. That would be in units of distance per time. And so maybe for this example, we'll say the units are meters per second. So let's think about what the units will be for this function. If we distribute the rho, because really in any given xy, it really is just a number. So if we do that, we're going to get f is going, and I'm not going to keep writing f of xy. We'll just understand that f, rho, m, and n are functions of xy. F is going to be equal to rho times m times the unit vector I plus rho times n times the unit vector j. Now, what are the units here? What's rho times m? What units are we going to get there? And we're going to get the same units when we do rho times n. Well, we're going to have, if we pick these particular units, we're going to have kilograms per meter squared times meters per second. So a little bit of dimensional analysis here. This meter in the numerator will cancel out with one of the meters in the denominator, and we are left with something kind of strange. Kilograms per meter second, which is essentially what if you view this vector has a magnitude in some direction, the magnitude component is going to have these units right over here. And then we're going to take this and we're dotting it with n. N just only gives us a direction. It is a unitless vector. It is only specifying a direction at any point in the curve. And so when I take a dot product with this, it's going to give us essentially what is the magnitude of f going in the direction of n. So this right over here, when you take the dot, it'll say it's essentially the magnitude, a part of the magnitude of f going in n's direction. And so it's going to have the same exact units as f. So the units of this part, you're going to have kilograms per meter second. And then we're going to, so let me make this very clear. So let's say we're focusing on this point right over here. F looks like that. Its magnitude, the length of that vector is going to be in kilograms per meter second. Then we have a normal vector right over there. And when you take the dot product, you're essentially saying what's the magnitude that's going in the normal direction. So essentially, what's the magnitude of that vector right over there? It's going to be in kilograms per meter second, and then we're multiplying it times ds. We're multiplying it times this infinitesimally small chunk of, or a little segment of the curve. We're going to multiply that times ds. Well, what are the units for ds? It's going to be a unit of length. We'll just go with meters. So this right over is going to be meters. So you're going to have, this whole integral, you're going to have kilogram per meter second times meters. So if you have kilograms per meter second, and you were to multiply that times meters, what do you get? Well, this meter is going to cancel with that meters, and then you get something that kind of starts to make sense. You have kilogram per second. And so this hopefully makes it clear what's going on here. This is telling us how much mass is crossing that little ds, that little section of the curve per second. And if you were to add up, and that's what integrals are all about, adding up an infinite number of these infinitesimally small ds's, if you were to add all of that up, you're going to get the value of this entire integral is going to be in kilograms per second. And it's essentially going to say how much mass is exiting this curve at any given point or at any given time. So this is mass, so this whole integral, let me rewrite it, of f dot n ds tells us the mass exiting the curve per second. And this should also be consistent. In the last video we saw that this is equivalent to, and this is where we kind of view it as a two-dimensional divergence theorem. In the last video we saw that this is equivalent to the double integral over the area of the divergence of f, which is essentially just, well, I could write two ways, the divergence of f, and this right over here, that's just the partial of, let me write it down here so that's some space, the partial of the I component with respect to x, right over here, I don't want to do this too fast and loose, so this right over here is going to be the partial of rho m, write it like this, rho m with respect to x plus the partial of the y component, rho n with respect to y, times each little chunk of area, times each little chunk of area. Well, what are the units of this going to be right over here? We know what rho m is. Rho m gives us kilogram per meter second. But if we were to take essentially the derivative with respect to meters again, the units here are going to give, the units for either of these characters are going to be kilograms per meter second per second, because we're taking the derivative with respect, per meter. We're taking the derivative with respect to another unit of distance. So you're going to take per meter, so you're going to have another meter right here in the denominator. That's going to be the units here, and then you're multiplying it times an area. You're multiplying it times an area, so that would be meter squared. That's right. This right over here is square meters. They cancel it out, and once again, this whole part right over here that you're summing up gives us kilograms per second. So you're having a bunch of kilograms per second, and you're just adding them up throughout this entire area right over here. So hopefully this makes a little bit more sense about kind of how to conceptualize this vector function f. If it confuses you, try your best to ignore it, I guess. But for me at least, this helped me out having a stronger conception of what vector f could kind of represent.